Perfect. Hello? Yes, we're working. Good afternoon. Big thank you to everyone that's come along. Great to see so many people here to learn about turbocharging our .NET code with some high-performance APIs that have been available for a while now, actually, but hopefully might be new to some of you in the room. My name's Steve. I'm a Microsoft MVP, Pluralsight author and engineer at Elastic. You can find me at Steve J. Gordon on most of the social media platforms, and I blog at stevejgordon.co.uk. And I will just highlight this resources link I've got at the bottom there. That will take you to a copy of the slides and also the GitHub repo where the code I'm going to show you is contained. So grab that link now, if you can. I'll leave it up for a second. I'll also show it again at the end for anyone that misses it. I'll talk about the next slide while you're taking photos. So I'm going to just briefly set the agenda and set the scene for what we're going to cover today. So the main things I'm going to talk about are a little bit about what is performance, because I want to make sure that we're all talking about the same thing and thinking about the same things as we go through this session. Then we'll talk a little bit about measuring performance in application code and why that's important. Then we'll start looking at some of the high-performance APIs that you can use for both efficient and low allocation code in .NET. So things like span of T, ArrayPools, a little bit about System.io pipelines, and at the end, hopefully, if I can get through it quick enough, we'll talk about System.Text.Json briefly as well. So the first thing is, what are we talking about when we're talking about performance in application code? The first thing I think of, and that most people tend to think about, is just how quickly the code executes, how long it takes for maybe the method or the entire process that you're doing in that code base, maybe processing a message from a queue. What is the execution time of that code? And it might be measured in a few seconds, it might be milliseconds, it could even be as low as nanoseconds when we start talking about specific portions of code. Typically, if we can make the code run faster, then it's going to have a better experience for our user base, and it might mean that we can get more work done on that machine. And that's where throughput as another measure comes in, because this is more about how much an actual application can do of a given task in a given time frame. So we might be talking about things like requests per second in an ASP.NET Core application, or maybe how many messages we can process off a service bus in a given frame of time with a given application. And this can be tied to execution time. If we can reduce the execution time of our code, sometimes we can increase our throughput. Not always, but they can be linked in that way. And throughput is just a sort of good measure that you can also track in production as well. And then the final aspect that not everyone thinks about when you start thinking about performance is around memory allocations. Memory allocations in .NET are very cheap. We have the heap pre-allocated block of memory that is being managed for us by the runtime, and it's basically just bumping a pointer when we allocate new objects on there. So that's very fast, very efficient, but at some point in time those objects are no longer used. A GC, a garbage collection process, needs to run to reclaim that memory. And although that's a highly efficient process, it's highly optimized, there's a lot of heuristics that go into how that runs to try and avoid pausing our application for any undue amounts of time, it's not entirely free. And so one of the things we can see in applications that allocate a lot, particularly larger objects, is we can see that those GC pause times start to impact the performance of high throughput applications. It's important also to point that performance is contextual, right? Not every application has the same performance requirements and characteristics. A lot of what I'm going to show you today doesn't apply to most applications in terms of the types of code that you might be writing, but in a few percent of your applications in high throughput systems, in areas where you're having to do a lot of processing and you have to have a lot of scale to achieve that, starting to look at optimizing your code can start to bring down the amount you have to scale your applications and potentially the costs that are associated with them. But it doesn't mean that you need to apply these code examples that I'm going to show you today in every scenario. There's also an important trade-off to warn you about when it comes to some of what I'm going to show you today, and we'll see this when we look at some of the more advanced code samples. There's a bit of a trade-off between the performant code and the readability of that code. And this can affect how easy it is to maintain applications. So if you've got a code base that's changing often, and it's being maintained by lots of different engineers within your business, it might be more important that the code's readable, concise and clear, and something that they can change very easily without having to worry about affecting the performance of the application. And so it might be more important that you focus on that readability of the code versus actually trying to highly optimize the code base for performance. But in those scenarios where you do need the performance, then you need to start accepting that trade-off that the code might become more verbose, slightly harder to read, and maybe only your senior engineers can sort of go in there and not be scared of that code base. Not sure why that's done that. Okay, so I wanted to talk about the optimization cycle. This is how we go about optimizing a sort of application that we already have. And the important starting point for any optimization is that we measure first. The reason we measure first is it gives us guidance as to where we should be focusing our time, and also gives us our starting measurements to see if the changes we're making are having a positive impact. So at the high level, this would be things like profiling the application, doing maybe CPU profiling to see where are the hot paths of your application under given workloads, what are the methods that get called most often, and of those, how long are some of those taking to execute, and then focusing in maybe also on the memory side and profiling the memory of those methods to understand where are the allocations that occur within them. Once you've got that, you can guide where you spend your time, because you want to be focusing on those hot paths. They're the ones that are going to give you the best gain if you can optimize them. Once you've measured and you've got that data, you want to start focusing on code level measurements. And this is where we start using things like benchmarking to measure the portions of code that we're going to change to see how those particular portions of code run. And that might be individual methods or even individual lines of code that we're starting to focus in on. But once we've got those starting point measurements, then we can actually do the optimization work. What you want to focus on is trying to do this in an iterative way and in small changes. If you make a whole heap of changes at once, applying a lot of high-performance techniques, and then you take your measurement afterwards, you don't know if all of those changes had a positive impact. Whereas if you change individual small pieces and then measure again, you can revalidate your assumptions as you go forward. So measure, do a small optimization, measure again, check that that has the impact you expect, and then move on and complete the cycle. And so this can continue as many times as you need until you get to either whatever goal you set yourself in terms of your optimization, or maybe you think there's no further gains for a particular method and you want to move on to a different area. It's quite easy to get trapped in optimization looking for really small gains at the kind of tail end of the optimization, and sometimes those don't give you a huge amount of value. So try and draw a line once you've achieved a reasonable amount of progress and look at other areas perhaps that will give you bigger wins. So how do we measure application performance? Well, there's several tools that we might have daily available to us. So if you're using Visual Studio and you turn on the diagnostic tools when you're debugging, you already have quite a good set of information. You can see when GCs are occurring, how much heap memory you're consuming in an application. You can take snapshots to see where that memory is being allocated. The only sort of caveat with this is that you are in debug mode, so you're not running the highly optimized runtime code base necessarily. So it's a good indicator, but it's not necessarily scientifically accurate for your runtime code. To do more accurate measurements on runtime code, you want to use either the Visual Studio profiling tools. There's a whole swathe of them now that you can use to analyze both memory, CPU time, async time, threading, etc. There's also Purview, which is an extremely advanced tool, very powerful, quite a steep learning curve. I haven't really conquered it yet in my own time. I use it a little bit and then kind of get a bit scared and move to things that I'm more familiar with. And I find that the JetBrains products, .trace, .memory for me, give a nice balance of exactly what I need to see, a nice user interface, and as I say, you get the measurements that you need that you can work with. But pick the tooling that works for you and works for you and your team, really. Sometimes, not often, but sometimes it can be useful to dig into the IL code as well. So when you compile C#, in most cases you're compiling to intermediate language code that then gets executed by the just-in-time compiler when you run your application. And sometimes you can view that IL code to get a view of how many IL instructions your code compiles down into. If you can reduce the instructions, often you reduce the execution time. And also you can look out for things like the boxing of value types. Sometimes those show up in IL tools as well. So these are all free, so you can grab that at any time and take a look at the IL code as well. And the important one not to forget is that it's always worth having production metrics and monitoring in place for your applications, particularly if you're doing optimization on an existing app. Because sometimes some of the optimizations we do in development don't necessarily translate to production. And sometimes they can even regress performance in production because it's hard to match that production workload in an environment where you're doing development. So having these measures in place before you start, things like requests per second, heap usage, maybe you're tracking the GC metrics, means that you can actually check once you deploy your changes, that you see the same sort of improvements that you were expecting. And I work for Elastic. We have a bunch of tools, including the Elastic APM agent or our new distro for OpenTelemetry that you can go and get for application performance monitoring needs, including metrics like the ones I discussed, or you can use any sort of vendor product that gives you the metrics you need to measure your applications. When it comes to the specific code level measurements, the tool of choice today is benchmark.net. This is a library for traditionally micro benchmarking. This is measuring small amounts of code and tracking the changes, even down to the nanosecond measurements. It can be used for more macro level measurements, but it's, as I say, sort of designed specifically for micro benchmarking scenarios. And it gives highly precise measurements. So you could, in theory, just put a stopwatch around some code and measure that a few times, and you would get a rough indicator of how long that code takes to execute. But doing that isn't that scientific. Whereas benchmark.net will do things like do a bunch of warm-up phases before it starts taking measurements to make sure that the code is JITted to the most optimized JIT version. It also makes sure it measures its own overhead to remove that from the measurements it's taking. And it will run each benchmark tens, even hundreds of thousands of times so that it can get a good statistical average of the data. Because if you're measuring down to nanosecond level measurements, anything else that happens on your machine, like an antivirus kicking in or another application starting up, could affect the measurements. So benchmark.net traditionally throws out the outliers to get you as accurate a number as it can for what you're measuring. You can do enrichment of data through this thing called diagnosers. There's a bunch of them in there, so we can get memory information during the benchmarking process. We can look at the JIT process. We can get a disassembly of the code. We can look at threading and ETW events as well. So there's a bunch of things you can collect during the benchmarking process if you want them. You can compare your benchmarks across different platforms, different architectures. You can try changing GC modes and see how that affects your results. And this is the tool that's used extensively within Microsoft for their benchmarking of the .NET runtime and the ASP.NET. So this is pretty much now the de facto tool for benchmarking .NET code. It's maintained by a bunch of people, including some people that work at Microsoft. So this is what a sort of hello world benchmark app might look like. So we have a program class here with a main method, and that's just invoking this static run method on the benchmark runner. And it's passing in the type that contains the benchmarks. Now, there's several ways you can configure benchmark.net to start up. You might have it do it where it automates all of the tests for you and runs every benchmark, or you can have it in an interactive mode where when you start it, you can choose which benchmarks you want to run. This hello world example will just run everything within that class. So our benchmark class is defined below. Regular class, I've added this attribute to say that I want to collect memory information through the memory diagnoser so that we can see how much memory is allocated while we're benchmarking. There's a bit of setup code. This isn't stuff that I want to benchmark. It's just stuff I need in place to perform the benchmark. So it's done, in this case, as static data. So we create an instance of this name parser, and we create an instance of a string that we're going to use. The actual benchmark itself is below, and it's a regular method, has the benchmark attribute on it. And then within there, the code there is what we're measuring. That's what we're going to get the measurement of the benchmark for. And in this case, it's this call to the getLastName method on that name parser. That's what we're measuring to see what its overhead is with that given input string. So we run this on our machine. We need to run this in release build. We traditionally, ideally, want to turn off every other application so that it doesn't interfere with the results. If you can disable antivirus, that's even better. It will take a while to run because it will, as I say, do all of those warm-up phases and then many thousands of runs to make sure it gets you good results. But eventually it will give you this report. And for our single benchmark, we can see a few results here. So the first is that we know that the mean execution time that it measured for that method was 116 nanoseconds. We don't know if that's necessarily good or bad. It's pretty fast. But that's our starting point knowledge about how long that method takes to execute. It also includes some memory information because I added the memory diagnoser. So this first column here gives us an indication of per 1,000 operations, how many Gen 0 collections might this introduce. Now this isn't 100% scientific because the garbage collection process is sort of tweaking itself all the time based on knowledge of your app at runtime. But this is saying basically it's around 29,000 operations before we would introduce enough Gen 0 data that might trigger a GC in this application. The important thing here is that we can tell we're not having any long-lived objects because there's nothing being reported for Gen 1 or Gen 2, so nothing would be promoted. So every allocation for this method is probably short-lived, and we can see the actual allocation amount there as 144 bytes. So this gives us, again, that indication, that starting point knowledge of how many bytes that code allocates in the process of executing. So we'll start looking at some of the high-performance code scenarios. And the first one I want to start with is span of t. Question I always like to ask is, how many people in the room have heard of span of t? It's a pretty good number, I'd say most. How many people have used it in a real-world application for something? Far, far fewer, which is also about what I expected. Maybe, I don't know, 5 to 10% of the room have maybe used it for something. That's kind of what I expect. So Microsoft talked a lot about this type when they introduced it, and they still do. The reason they talk about it a lot is because it introduced massive improvements to what they could optimize in the .NET runtime itself. So this sort of opened the door for some of the work that's happened since kind of .NET Core 2.1 era for all of those high-performance things. And if any of you look at sort of like Stephen Taub's blog posts every year, where he talks about all the high-performance optimizations and where they've reduced memory allocations or increased the performance of code, a lot of that starts to talk back to the fact that span of t exists because it opened the door for that. But also, not many people have used it, and I think partly because Microsoft did caution against most developers needing to use span of t in their code bases. That message has been, I think, dulled down a bit now, and I agree, it shouldn't be the general message. I think this has its uses, and as you'll see in the code, it doesn't necessarily always make it overly complex and can give you quite good wins. So what span of t, when span of t was introduced, it was built into .NET Core 2.1. So that's like 6 years ago now. So it's been around a while. It was also released as a NuGet package, so System.Memory that you can bring into framework applications as well. The optimizations aren't quite as sufficient or efficient, sorry, on framework because there were runtime changes made in .NET Core to get the full performance gains, but it's still a pretty good use case even if you're using framework apps. Ultimately, what span of t does is provide a read-write view over some contiguous region of memory. The important thing is that it doesn't care where that memory is. So it doesn't mind if that memory is on the heap. Traditional contiguous regions of memory would be things like strings or arrays, which are a block of memory on the heap. But it can also reference stack allocated memory and even unmanaged native memory. But all through a single API. And it does this in a type-safe, memory-safe way, so you don't have to think about all of the possible caveats with doing that and drop down to unsafe code. It's all safe code that you don't have to have those unsafe keywords to use. You can iterate through this contiguous memory, you can index through it, you can sort of parse through it, just as you would with a traditional array, really. And it's almost as efficient. Like there's maybe like sub-single-digit nanosecond performance overhead for having a span versus a native array, but a lot of work went into making this highly efficient in Core CLR in particular. So one of the key operations once you've got a span is this idea of slicing. So slicing is really just changing the view over an existing block of memory. So in this scenario, we start by creating a new array of 9 elements. We then call asSpan to get the span representation of that memory. You'll see it returns a span of int. You might there be thinking, oh, well, that's an allocation. We've got a problem. But actually, span is a type that's guaranteed never to be heap allocated. And we'll talk a little bit more about why and how. But the main thing is that there's no heap allocation cost. There's no overhead to creating this span. So it's a highly efficient type. So once we've got our span, we can do something like slicing. And slicing just takes a start position and optionally a length for how we want to slice that data. And it just returns the same data that exists already in that memory region, but sliced to that new view. I kind of give the analogy of this of photography. So if any of you, take photographs when you visit a new city, we've been out, my family and I, in Oslo. We've taken some nice pictures from across the water of the Opera House. And then at some point in time, we think, actually, it'd be nice to see that a bit closer. So one option is that we could walk around the waterfront, we can get closer, and we can take a nice close-up image. But it takes some time, takes some effort. Or we can just pinch zoom on our camera, and most of the time that gives us the view we want, and it takes almost no time at all. And that's kind of what slicing is. We've already got the data, we're just changing our view over it. And the important thing about slicing is it's a constant time, constant cost operation, an O of 1. And so this means that even if that array is 9 elements or 9 million elements, slicing just takes the same amount of time, because we're not creating any new memory, we're not copying memory, we're just changing a view over it. So let's look at optimizing some code. I will warn you, this first example is extremely contrived and trivial, just to get the point across. We'll look at some more real-world code shortly. But imagine that tomorrow or Monday when you return to the office, your manager comes to you and says, look, if we can develop a method that accepts an array of even number elements that can, we can return a quarter of those elements starting from the middle, we're going to make some money somehow. Probably not, but let's imagine that's the scenario that you're given. I'm sure you're all hoping that's the most complex thing you're given on Monday morning. Many developers, given something like that, might opt to just use something like link, where you get the existing length, and then you say, well, we'll skip halfway into that, we'll take a quarter of the elements, and then we'll just return the array, and job done, right? And that's fine. That's reasonable code for the requirement that's been given, but then our manager comes to us and says, hang on, no, we can make a lot more money if you can make this quicker. So let's go ahead and think about that. So the first thing, as we learned earlier, is that we should measure before we make any assumptions about what we're doing. So here, this is a slightly more advanced version of benchmarking. So this is our setup for our benchmarks. So the first new thing on this slide is this size parameter, or size property that has a params attribute. And this has 3 different values. And what this allows us to do is say to benchmark.net, we want you to run this benchmark 3 times with these 3 different sizes. And this is important in benchmarking because you can often get tricked by just testing one scenario and assuming that's giving us like the coverage for our entire possibilities of what could happen in our application. So it's best to test around the edges as well. So maybe we always assume that our array is going to be about 1,000 elements, but sometimes it can be a little bit bigger or a little bit smaller. So we start to measure both sides just to see if our changes apply in all scenarios. So once we've set that up, we need a way of populating that array. And so this setup method here, which is attributed with global setup, is basically going to run once per benchmark, and it just allows us to initialize the array of the right size based on that size property that will be populated by benchmark.net, and then just fill it up. So none of this contributes to the measurement of the benchmark. It's all setup work. The actual benchmark is very simple. We're just testing that link code that we had. The only difference from the last example is that we now have this baseline equals true set on there, which says this is our starting point. So all other benchmark measurements will be benchmarked against this. And so when we run this, we get 3 results this time, 1 for each of those different sizes. And we can see that, okay, it's about 100 nanoseconds on 100 elements, and we allocated 224 bytes. It got slower for the next size up, and it allocated a bit more. And again, factors more increase in execution time and allocations as we go up. Not that unexpected. We're creating a new array and we're filling it up. And the bigger the size, the bigger the array, the more copying needed. So the first theory that one of our engineers has is, well, I've heard that link can have some overhead to it. So maybe we shouldn't use link and we should try and avoid that. So we can do that by just creating a new array of the appropriate size, using something like array.copy to copy the memory in from the appropriate point, and then just return the new array. And so we measure this, and for the first result of 100 elements, 86% reduction in execution time. That sounds good. And it looks like we've almost halved our allocations. So on that row alone, it looks pretty good. But we can see that for 1,000 elements, the execution time gain is still there, but the allocation gain is far less significant. And as we drop down to 10,000 elements, we're now only 1% improved. And that's because all we've really shaved off is the 96 bytes of link overhead of the expression being compiled down. But everything else, you know, we're still creating an array, we're still having to copy memory, and so there's still the allocations from that. So the final option, and this is where the example's a bit contrived and trivial, assumes that we can change our return type of this method or introduce a new method that returns a span, and our caller can work with that. But if they can, then we can just drop down to slicing the existing memory to change the view so that our caller can then work with that piece of memory and do some further processing. And so in this scenario, we're just add span and then slice. So then when we're using span on my machine, that's less than a nanosecond on the measurement, so a pretty dramatic execution time improvement, and we've not got any allocation cost. We've not created any new array to return. We've just given someone a new view over that existing data. And you can see that that then is roughly consistent. When we're down to sub-nanosecond measurements, the variation is quite significant. But about 0.6, 0.7 on my machine nanoseconds for that to run. And this is where we can see that regardless of the array size that goes in, there's a constant time, constant cost operation to slicing that data and changing the view on it. We can also work with strings using spans, so we can call as_span on a string literal or on a variable that points to a string, and that returns to us a read-only span of char. So char because strings are made up of characters, so that's the element that we're going to look at, and read-only because strings are immutable. And if we were given a span that's a read-write view over the memory contained by the string, we could break that immutability of strings and basically break every app's assumptions everywhere, and probably most apps would fall apart. So the runtime enforces this read-only nature where we can view that string's memory, we can parse our way through it, we can sort of learn and process that string's memory, but we can't change the characters. And so once we do that, we could do something like, in this trivial example, say if we wanted to just get the data that represents the surname, we could find the index of the last space in this string and then slice from there, and then we're viewing the surname portion, and we could do some further processing. Now, on this string, this isn't going to give you a huge advantage over using something like string split, but on a large string, processing with spans can be really optimal. Now, there are some important limitations of span that it's worth highlighting. I'll come back to that point I mentioned earlier where I said that span can never be allocated on the heap. And it's done and enforced through this new keyword that was introduced in C# 7.2, where we have this ref struct type now. So regular struct types, as most of you know, will generally end up being stack allocated, but there are various ways that they could either be boxed onto the heap, or they could be contained in an object that's stored on the heap, and so that memory is on the heap. Ref structs are enforced by the runtime that can never happen. And that's important because it might point at stack allocated memory. So we don't want this span to outlive the memory that it's giving you a view over. And there's various other sort of internal implementation details about why this matters around struct tearing and the sort of bioref-like nature of these types that could introduce overhead for the GC as well. But by enforcing them as this special ref struct, all of those risks go away, and that means the team could optimize the type very well. But it does mean that the type cannot be boxed, which can be a problem. It can't be a field in a regular class, because that class is on the heap and its data structures are also therefore on the heap. And it can't be a field in a regular struct, because that could be boxed onto the heap. It can't be used as an argument or a local within an async method. This is the one that probably most people are concerned about, and we'll see how you work around it in a moment. This is important because those async methods end up being sort of recompiled behind the scenes to state machine classes or structs, and those, again, sort of break the earlier rules because any of those locals or arguments end up as fields on those state machines. For a similar reason, it can't be captured inside a lambda expression because of the closure types that get generated. Can't be used as a generic type argument, and there's more. So at this point, you're probably thinking, well, hang on, this is really, really limited. Where can I actually use this thing? But it's most places you can work around most of these. And that's because there's a sister type called memory of t, which has a lot of the same APIs and doesn't have quite the same requirements, so it can live on the heap. It's slightly less versatile than using span, and it's slightly less performant. It's defined as a read-only struct, not a ref struct. So doing things like slicing into a memory of t is slightly slower than compared to span. But at any point in time, once you've got that memory of t, you can call it span property and then get the span representation of the data that it's looking at. And so what this means is, in this scenario, say, where we want to have this async method accept a span of byte here, the compiler is upset and says, no, you can't, for the reasons I've already discussed. And so what we can do in this method, our signature here can accept a memory of byte instead. And so what our code could do is just work with that. And it's got the same APIs for slicing as we saw with span. Or if we do really want to highly optimize this code and rely on span, we can create a non-async method that does accept a span of byte and then call into that at any point we're outside of the async flow of that code. Because async is only really needed for I/O. You're calling, network sockets, or you're reading from files. But as soon as you've got that data and it's buffered into memory in some form, inside a stream or a memory stream or something, at that point you can switch to non-async code. And so in this application here, the first thought might be that you could create a local. Well, you can't, by slicing the data that you want to pass in there. So the way we work around this is just passing directly that slice expression in, and this is totally fine for the compiler, and it can handle all of that. And all of our optimized code can be span-based in that non-async method. So I want to put this one into practice with a slightly more real-world example. So Actually, if I just go through this slide, just so that you know what the example talks about, that would help. So this comes from a previous job I worked at where we did a lot of message and event-driven microservices that were processing stuff. And so in this sample, it read from a SQS queue, read the message, it needed to deserialize that message, and then we basically stored a copy of the JSON message onto S3, which is the Amazon Blob Store. And to form the object key, which is basically the file name, the unique file name on there, we use certain properties from the message to derive the object key. And so I promise we did all of the things I said. We benchmarked, we measured, we profiled before we did the work, and I'll show you the results afterwards. But this is, it's not the exact code, but it's close to what was in the original application. So the first thing is this accepts this event context here. So this is basically the deserialized JSON message from the SQS queue. In this example, it has a few properties. In the real example, it had several hundred. But we were only using a few of them to derive the object key. There was a caveat in the app at the time that we didn't always guarantee that there would be a date on one of the fields, so we had to handle that scenario. So I've kept that in because it keeps the example a bit more real world. So basically, the original code worked out if the date was present, we were going to have 5 elements making up the object key, otherwise it would be 4. We then created a string array of that number of elements, so we were going to hold 5 strings or 4 strings, depending on that scenario. And then we populated each of those elements in that array of strings using this getPart method, taking a string. GetPart basically did a quick null or empty check to check if the input was null or empty, and if it was, it would use unknown as the value in its place. We then remove the spaces, and remove spaces down here just used string replace, so remove the space character and replace it with an underscore. And then the isPartValid code was just using basically a regex match to say, is this a valid values that can be used in an object key in AWS? And if not, we'd use an invalid part, otherwise it would return the part. So this would build up those this array of strings that we're going to form the portions of the object key where we're going to populate. We'd also, if the date was present, just do a toString on there to get the string elements that we wanted in there. The final element was the message ID with the JSON suffix. And then these were joined using string join to join all those elements together with the slash character as the separator, and then it was lowercase, and then that produced the object key. So a lot of you might be able to spot where there would be some intermediate allocations in this code. For most apps, that's probably okay. In our scenario, we wanted to try and work around some of those costs. And so in this code, which if I just scroll it first, so the new code is a little more verbose, but not too much more. There's some weird stuff that goes on at the top. So the first thing, so I've updated this demo. At the time I did it, we were doing it in I think it was .NET 3.1, I want to say. But I've updated this code recently for .NET 8. So I'm taking advantage of regex source generators here, which is one of the gains that Stephen Taub has talked about around where the compiler does the regex work up front as part of the compilation process rather than at runtime through reflection, and that's going to give you quite a good performance gain. This weird stuff here, this static read-only span of char with this array, or what looks like array of characters, is a special optimization that the compiler has and the runtime has around storing this data into the metadata, into the kind of blob of the binary, so that we don't have any heap allocations. And these are basically just some of the constructed string values that I want to use, like the invalid and the unknown, that we can optimize in. The main work happens down here. The first thing that happens is the length is calculated. So I'm using a feature here called String.Create. What this basically lets us do is create or essentially mutate individual characters of the memory of a string during its creation, which allows us to use high-performance techniques like span. But it's before the string's returned, which is why we're allowed to sort of mutate that data. But we need to know how long that string is going to be up front. So this calculate length, which I don't need to show you, just does that. And then String.Create takes that length, so it can pre-allocate some memory for the characters. It takes in some state, in this case our event context, and then it takes in this special span action, this key builder action from down below, which is an action here of characters and the event context. So ultimately what this means is that we get access to this span that represents the memory for the string in a read-write form and our data. And so what we're doing here is we start by starting at position 0. We do a build part, taking in our input data for the first piece of the object key, the span that we're writing into, and then the current position. In build part, what that did is basically do the same checks we did in the previous code, but we're using a higher performance technique. So rather than is null or empty, we just check the length is, if the length is 0, or using this memory extensions, all of the data is white space, then we use unknown. So that unknown part data that we stored in the blob gets copied into our span. Otherwise, the validation regex gets called. And then eventually, if it's valid, we use this memory extensions toLower invariant to basically copy from our input string into the span and lowercase at the same time. And the span that we're writing into, we're using this range operator behind here to move our way through it. So as we write each object key in, we're going to update our position, or part of the object key, we update our position by updating the length here. For the date, we use try format, which also accepts the span as the destination. So this is an optimized version of essentially toString on a date. This takes the format that we want to use. It returns the bytes written that we can use again to update how far we've written into that span. We copy in the message ID, and then finally, 5 characters from the end, we copy in the JSON suffix. So basically, all this code has moved us to is to using span as a method for writing our string. And as we'll see in the results, this does actually lead to some performance gains. So in the original code, this was taking around 300 nanoseconds to run. And you can see that we've made a 26% improvement on that by moving to this. Now, we weren't really looking for execution time gains. We were mostly focused on allocations. And so we can see that actually the allocation reduction on this is about 74%. So from 728 bytes down to 192. You might be thinking, is that useful? But at scale, this was doing around 18 million messages a day. So that's 10 gig of allocations in this service just for this piece of code alone that we dropped out by doing this. And that actually meant that we did see a reduction in sort of Gen 0 heap collections from the garbage collector. The actual benefits were far better at the time we did this at 3.1. I think the ratio of performance improvement was near 80% on the execution time. But .NET 8's got so much improved that the gains in this benchmark are starting to go away. So you don't have to necessarily change your code as much to get the gains from .NET as you did when we wrote that original code. The next type that I want to look at is the ArrayPool. The name kind of gives this away. It's a pool of arrays for reuse. So in a lot of applications, you might have scenarios where you're allocating an array, a short-lived array, for some kind of buffer, particularly if you're doing using the streaming APIs, you need these buffers that you pass in. But it can happen all over code bases where you just need a block of bytes or a block of characters, and you're doing some work within that data and ultimately producing a string or passing that data somewhere else. By using ArrayPool, we can get the advantage of just avoiding those short-lived allocations. And the pool means that we are going to use arrays that are going to be shared amongst other areas of our application. And this basically means that we can amortize the cost of those short-lived allocations. So you do end up with slightly more long-lived objects that will eventually end up in Gen 2 because they will be held by the pool and reused. But in most applications, that will be worthwhile because you'll be seeing far fewer short-lived allocations of those. So this is found in the system buffers namespace. There's a shared implementation, which is the one you're recommended to use for most scenarios. So you call ArrayPool of T shared, and then you rent from that the array that you want, the length that you want. The important thing to tell you is that you are likely to get an array that's larger than that length, which might at first sound a bit weird, but that's kind of how the array pool is optimized. If it could return you an array of any length, then it's going to be pooling a lot of arrays that will never be reused across other parts of the app. So it has different bucket sizes of arrays that it's going to try and find the most suitable one from that it can hand out to you to use. When we're done with it, we return the array to the array pool. We can optionally clear it. So by default, the array isn't cleared, which is, again, something to be aware of. So any data that you've written into that array will then be visible to whoever rents it next. And it also means that when you're renting arrays, you need to be aware of it because, again, you don't necessarily want to read all of that data assuming you've written it. And so when you work with arrays that are rented from the pool, you do need to track how much data you've written into it, how many elements of that have you, from 0 have you actually filled. And then typically what you're going to do is slice to that position when you're then processing that data. And that ensures that your code base is only ever reading the portion of that rented array that you know is your own data. So that's, yeah, an important warning that can trip a few people up. But otherwise, switching to ArrayPools is pretty trivial. And so in this, again, very simplified example, we have a method that's going to get called very often by some of our code, maybe from a loop somewhere further up. And in there, it needs to create a byte array of 1,000 elements that it passes into another method, then does some processing using that buffer. Now, this code obviously allocates that array every time. So if it is called from a tight loop, we're going to create these short-lived 1,000-byte arrays fairly regularly. So we can switch away from that by instead moving to using the shared array pool and then renting. So in this case, we rent 1,000. Now, because of the way the shared array pool is implemented, I know that the first bucket size that could possibly fulfill that need is going to be 1,024 elements long. But it might be even bigger than that. If the next size up happens to have a free array and 1024 is already empty in the array pool, then it might give you a larger one. So we need to make sure that in our code further down that we are tracking our position within that array and either slicing it or processing only the portion of it that we're writing into. We also need to make sure that we return it, because otherwise what's the point of having an array pool if the data just is going to never be returned to the pool. So typically the pattern for doing this is using a try finally block to make sure that we always return it. The next type I want to touch on, I won't go too deep into this because it's a little bit more niche where you might use this, but System.io pipelines was introduced originally by the ASP.NET Core team. So their main scenario is that they're in their Kestrel web server for ASP.NET Core, they're receiving a lot of bytes off the wire, and then those have to be parsed for the HTTP content to then further process that within ASP.NET Core. And so that process means traditionally that would go through a number of sort of intermediary streams within ASP.NET Core. The team worked out that they could optimize all of that stream usage to try and remove a lot of the overhead and the allocations, but it was a lot of complex code. And so what they did is package that up into this pipelines package that, in their scenario, at least for ASP.NET Core, was giving them around a 2x performance over using traditional streams in the kind of traditional way. But as I say, it's packaged up for us so that we can reuse that same sort of improvement if we're doing streaming data without having to write that code ourselves. We could technically write it, but it's a lot of boilerplate, and so it's just available in this package. The main difference versus using streams yourself for this stuff is that with streams you create the buffers, you create the memory that you pass into them, and then the data is handled within those streams. Pipeline does all of the buffer management for you, and so it can optimize that. It uses the array pool for where it's getting that data, or that memory for you, and it ensures that that's all sort of returned as soon as possible behind the scenes. There's, as you might assume, two ends to a pipe. There's a writing end and a reading end. So on the writing side, what we get is this pipe writer. On pipe writer, the first thing we do is ask the pipe writer to give us some memory. So we call get memory. This returns a memory of byte. So why memory of byte? Well, traditionally, at the point you're filling these pipelines, you're in an async context. And so we probably can't have a local of span there because we're likely to be in an async method reading off of a network, or off of a file or something. So we get memory of byte, but you can use the same techniques I showed you earlier to switch to non-async code and span for filling that if you want to. Once you've written some data in, you advance by the number of bytes that have been written, and then you flush in an async way. So that flushes the data into the pipe. On the reading end, the reader has this read async method that we can call, and so this is a non-blocking way of saying, as soon as there's data in this pipe available, give me the data that's been written or flushed in so that I can start processing it, so that we can highly efficiently stream through this data with both ends sort of reading and writing at the same time. The read async method returns a read result, and on the read result we can access this thing called a buffer, and this gives us this read-only sequence of byte. So why read-only sequence of byte on the way out but a memory on the way in? The main reason is that the pipe in advance doesn't know how much data you're going to give it. So it's going to rent some memory from the array pool, but it's going to sort of pick a block of memory that's available and start filling it. But you might stream 100 bytes, or you might stream 100,000 bytes off the network. And so at some point, that little block of memory that's been rented could fill up. And so internally, what this looks like is basically the pipe during the writing side is just going to keep renting these blocks, returning them as memories of T to you that you're filling up. But it handles all of that internally. And then on the reading end, what it gives you is essentially a linked list of those blocks of memory, referred to as this read-only sequence. And so that's the data that you can then parse through in the correct order. So the next scenario that sort of demonstrates this, again from a previous role and from pretty much the same microservice, I think, was where we were receiving an object from S3, the blob store in AWS. It was a tab-separated file in sort of compressed format, and so our job was to open the file, decompress it, and parse out 3 of the 25 columns within there that were going to then be stored as an object into Elasticsearch. So again, I'll show you the before and after code just so that we can kind of get a feel for what that looks like. So the before code is actually pretty terse. It's just that block of code there. If you're reading ahead of what I'm talking about, you'll probably start seeing where there are problems here. So this was written by a colleague. We hadn't noticed this code going in. The first indication that this service had some memory issues was that it was starting to hit container limits. So this was running as a scaled container, and we had a sort of reasonably high memory limit set, but we kept hitting that. And we were like, well, this doesn't make any sense. We keep increasing the memory limit, and we keep hitting it. So we looked at the code, and you can kind of see the problem if you stare at it. So in this case, I'm using a file stream rather than AWS, but basically if you read a file from AWS, you get back a stream. We then use gzip to decompress it. That's fair enough. Where things got a little weird was this creation of a memory stream, and then this copy from the decompressed stream into the memory stream. Sorry, that's happening here. And then this decompressed stream that we've copied into is then cast to an array or stored as an array in order to pass it into UTF encoding, UTF-8 to get a string. So at this point, we've ended up, after various copies of this memory, with a string that represents the entire contents of the file. These files were 10 to 20,000 lines long of tab-separated data, so that's a reasonably large string. So all of these are actually large object heap style allocations. Then that data was passed into this CloudWatch parser, and the reason I think at the time for the string allocation stuff was that the author of this code was using tiny CSV parser, which I think at the time maybe only dealt with strings. I'm sure it doesn't now. This tiny CSV parser made it very easy to parse CSV or tab-separated files by basically using this sort of link style syntax here to read through, split on the lines, and then had this mapping syntax down below to say map me from these columns 0, 1, and 10 onto this object and give me the object back. So it's quite simple code that's easy to use because of the use of this library. But if you look at, just look at the code above, you can kind of see where there's a lot of copying going on. So we had a crack at rewriting this, and the new code is a little bit longer. It might be a little harder to understand what it's doing, but we optimized away a lot of the overhead. So we still have to decompress the file, so that still kind of happens as before. But as soon as we got that decompression stream, we used pipe reader create here to actually start creating a pipe. Now, strictly speaking, probably didn't need a pipe in this scenario because we only dealt with that data once. But actually, we did think we were going to do some further processing through further parts of that pipe reading process that made it more reasonable at the time. But it uses the same code that we just looked at. So we call read async, we access the buffer once we've got some data, and then this parse line method here takes that buffer. The buffer is that read-only sequence of byte. To make it easier to work with these sequences, because there's a little bit of complexity about understanding if there's one element within there or multiple parts to that sequence, this sequence reader struct was introduced, and we can create an instance of that to help us read through the sequence. So that has convenience methods on it like try read to any. So we can say try read to any instance of a new line character. And if you find that, we know we've got enough data within this current sequence that gives us a line from the file. And so it returns us that line. And so this loop here is basically going to read until there's nothing further available from that sequence reader. If we don't have a line, we break, and then we wait for more data to be flushed in. But once we have at least enough data for one line, we can parse it. And at this point, we're working with a read-only span of those bytes. And then this new code basically pre-creates the type that's going to be stored into Elasticsearch that gets populated with this code. It then loops, checking for the index of the tab character, and then it takes the strings that we need, the 3 columns we care about. So at tab count 0, 1, and 10, we're going to extract the string by slicing that data that precedes that tab character. This code below is just going to update our view over that line as we move forward. So it keeps slicing it. So as we slice the tab, it gives us a new view containing the remainder. And then we update the tab count on each iteration. And this loop can break after we've read the first 11 tabs, because that's the ones we care about. After that, we don't need to parse the file or the line any further. That's pretty much it for the code. So I'll go over to the results. So in the original processing or benchmarking of this, we used one file of 10,000 rows to give us a vaguely reasonable real-world measurement of the overhead. So you can see that the execution time has gone down, but we're still only talking milliseconds. So execution time wasn't our issue, but we've got a nice 80% gain anyway. The issue for us was the allocations, and you can see over here that original code just for that one file is allocating 100 megabytes. As I say, most of those on the large object heap as well, requiring a Gen 2 collection later on to clear them up. As you can see from the numbers in that Gen 2 column, there's a lot more allocations occurring in Gen 2 in that original benchmark. In the new example, we were down to 3.32 meg, so a good 97% reduction. You might think, oh, well, 3.32 meg is still pretty high, but actually, once we then did memory profiling of the optimized code, we checked, and actually 2.85 are the strings that we expect to create. We needed 3 strings from each object, from each row, that we then use to create the object that we store into Elasticsearch, and at the time, those were unavoidable. So those we accept. The remaining overhead, 0.45 meg, some of that's coming from pipelines, some of that somewhere else. I was quite keen to dig deeper, but a colleague pulled me back and said, actually, we don't care about that little extra allocation. I wish I still had access to the code, because I'm still curious to see if we could get down to nearly 0 overhead. But sometimes, as I say, once you've optimized to a certain point, your goal's achieved, moved on. So I thank my colleague for stopping me going down that rabbit hole. So the final API is System.Text.Json. How are we doing on time? Good, we're doing well. So we'll quickly talk about System.Text.Json. So this again has been introduced around for a while. This was introduced, I think, in Netcore 3.0, and it's a new set of in-the-box APIs for working with JSON data. I think most people have probably heard about them now. At the time, there was a big controversy because we had JSON, nice open source library for JSON processing that nearly every app used if it worked with JSON. And this was a sort of a flag that Microsoft was sort of stamping on open source and creating their own thing. Now, James Newton King, who created JSON, did sort of validate that this had merit. Now, partly he was employed by Microsoft already at that point, so maybe he had to say that. But there were some good reasons. So one of the things was JSON was written well before things like span of T and pipelines were available. And so it would be a big rewrite to fully optimize it using those new concepts. The other thing was, by this point in time, JSON has really kind of become de facto in most applications. Many apps, particularly ASP.NET Core apps that are doing web APIs, for example, they're all going to be needing some kind of JSON parsing. And so having something in the box from .NET, supported by Microsoft, optimized and maintained by Microsoft, does have some merit in that regard, because it's quite an important set of APIs that most other languages or most other frameworks package for you. But whether or not you're happy with the idea, the performance gains do tend to make it worthwhile. So it's made up actually of 3 main levels. There's this low-level APIs, the UTF-8 JSON reader and the UTF-8 JSON writer. If you drop down this far, you can get to almost or generally 0 allocation overhead sometimes on parsing bytes of JSON data in an application. But as we'll see when we look at the demo, it can be quite complex or quite deep code. There's a mid-level offered for reading JSON data in this JSON document format, so that allows us to more easily work our way through a JSON document format, looking at the elements that we want to find, locating a particular property within a structure of JSON in a quite efficient sort of single read way. And then there's this high-level API, JSON serializer, and on there we have the things like serialize async and deserialize async, the traditional types of APIs you'd expect from a JSON library. Most people will just use the high level, and that will give you generally performance gains over something like Newtonsoft.json, because under the hood it's already been rewritten to use things like spans and pipelines and efficient sort of memory processing behind the scenes. And so just by switching to this library, you can get the gains. It used to be the case that the APIs in System.Text.Json were quite limited. Since that sort of 3.0 timeframe, the team have really sort of built on them, and so a lot of the functionality that was available in Newtonsoft.json is now possible in System.Text.Json. I'm not saying the APIs are 100% compatible. You're going to have to rewrite your code and update it if you do the migration, but most of what you needed to do is probably possible now. So to put this one into sort of practice. The example we had for this was we were, at the time, working with Elasticsearch, and we were indexing a lot of data from these messages into Elasticsearch. And we used its bulk API to do that. And in short, the bulk API allows you to send a new line delimited set of JSON data of operations to perform. So rather than sending a write request for every document you want to store, every sort of piece of data you want to store, you could package those up into 100 or 1,000 write operations to send in one HTTP call. And so you're reducing your HTTP overhead quite significantly if you've got a lot of data to index. This bulk API returns you a JSON response, and on that response it tells you, did any of those operations fail? Because it's going to try and do all of them for you, and if one of them fails, but 99 out of 100 succeed, you need to know about that. And so you need to check that errors property to see if there were errors. It tells you also how long it all took, and it gives you the detail for each item, for each operation, the specific details of its success or failure, status codes and things. So what we needed to do is check that bulk response and look at all the IDs that failed so that we could put them into essentially a dead letter queue for further investigation. Didn't expect that to happen very often, but it was still needed to be considered. So, don't want to steal the thunder and give you the results early. I want to show you the code. So the original code for this is like super. It fits on one screen, even at this stupid font size. So basically, this is Newtonsoft.Json, so we ultimately ended up creating this JSON serializer and deserialize using that into this bulk response. So this says, give me the bytes that have come over the wire and then deserialize them into this type. And you can see it has how long it took, the errors, and then the items, which would be the results for each operation. So we first deserialize that response into that object model. We then check, were there any errors? So if there were no errors, then this method, which returns this value tuple here, can return success true and an empty string for the errors that were reported. So in the happy path, which we expect most of the time, that's what's going to happen. If there were errors, then we need to look through the items that were returned, find those with the 400 status code, for example, find the IDs, and then return those so that we can identify which of those messages failed. So pretty terse code, pretty straightforward. The new code, as you can see, is longer. And this is why this is important around this readability versus maintainability. If you don't need to optimize and Newtonsoft.Json is working fine and the app's perfectly happy, probably stick with it, or at most switch to the high-level API of System.Text.Json. But if you really want to try and get the high performance, as we did, just for an exercise, I think, at the time, then what we do is basically, we're working with the streaming API. We could have used pipelines here, but we're using the ArrayPool to rent a buffer. It's hard-coded in the demo because I know how much the data is going to be. We read from the stream into that buffer. Ultimately, then we go into this parse errors code here, which takes a bunch of state, essentially. And then it uses the low-level UTF-8 JSON reader API here to start reading from that read-only span of bytes from the JSON data bytes. And so what this does, it's a reentrant type, so it can take some state of its own, so you can keep calling it if you're streaming data as you're getting more bytes from the wire. And what you can do on there is call read to read the next JSON token. And then in here, this code is basically switching then on specific JSON tokens like start object, start array, etc. And because we know the structure of the JSON we're expecting, we can highly optimize this code. And so basically what this is doing is working its way through, tracking its position until we've read a property which has got the name errors. So we know we found the errors property. And once we've got that, which we set the states of flag that we have that, once we're in this, the next token we're going to get is either true or false, the value for that. And so we're hoping that it's going to be errors false. And at that point, we can set this other piece of state. And so what this code will do is break. Once we've found the errors property and we've found that there are no errors, it breaks. Otherwise, it has to keep going because it's going to need to read all the items to find all of the IDs of the failures. But that's essentially, I won't go through all of the code, what that's doing. And so this code above then, after reading part of the data that's been streamed in, if we found the errors and there are no errors, we don't even stream the rest of the data because we know we don't care about it and we can just stop streaming. In other scenarios, we have to stream further. So quickly show you the results before I wrap up. So in the failure scenario, the improvement optimizer code was 67% in execution time. Again, mostly we were concerned on allocations. And you can see we've gone from about 100K to about 16K allocation overhead. But that's the failure response. That's the response we don't expect very often. The one we do expect most of the time is that it succeeds, and that's what we wanted to optimize for. And so in that scenario, because of that short-circuiting code that basically just ends up reading the first property of JSON that comes back and then breaking out and no longer streaming it, we're down 99.9% in execution time because we just short-circuit in 200 nanoseconds out of this processing code. And the overhead's now 0 because we've already streamed the data. The actual processing overhead is 0 because we're just reading through those tokens using the low-level API. So that was a pretty good gain that we could get there by dropping to those. So I've got like a minute or so left. So quickly to say how we get business buy-in to do this. You maybe like what you've seen today. So when you go back to your office, start thinking about where you've got quick wins. Have you got an app that's always, people are always complaining about how slow it is or how slow a particular part of it is? Maybe that's somewhere to look at optimizing. Be scientific about how you do it. So, get the benchmarks, get the profiling to validate where you should improve and how long the existing code takes to run. If you're going to then business management, though, don't just say, I can save 87% of the byte allocations on this method, because most managers above engineering are probably going to go, yeah, I don't care. So show them some money they can save, give them a cost-to-benefit ratio. So a very basic example of that, for the service we were looking at, where we could use a lot of the examples I've shown you today, we worked out we could reduce about 50% of our allocations using those techniques, and that we could roughly double our per instance throughput of those container services when they were doing processing. What that ultimately led to is saying that we could drop one VM from the cluster a year that was under that container cluster, saving about $1,700. That might not be enough to justify the engineering time that went into it, so do be aware of that. But if this can be scaled in our microservice environment where we had hundreds of these doing very similar things, then we worked out that maybe we could save it 10x or 100x times across those services, and that gain might be more important. And my daughter's coming to the stage. Hello. Yeah, Daddy's nearly finished. So, quick summary. Bye-bye. Sorry about that. So the important thing is when you're doing your code, do you want to come here? Yes, OK. Measure your code. Don't assume. Don't make assumptions with benchmarks. It's dangerous. Be scientific about how you analyze the results. So use techniques that are like benchmark.net to get you proper measurements. Yeah. Focus on the hot paths. I'm glad she's agreeing. Focus on the hot paths. Don't spend your time on methods that are called once or twice in your application lifetime. Those hot paths are where you want to focus on the time. Don't copy memory, slice it, and that will ensure that you're avoiding a lot of the overhead and the time spent working with that data. ArrayPools are really useful and an easy switch to avoid short-lived array allocations. Yes. Pipelines can be quite good if you're in a niche scenario where you do a lot of data streaming. And consider System.Text.Json APIs for high-performance JSON data. So the last thing I want to show you is this book. I learned a lot of the techniques about memory management from this book. It's about that thick. It's about 1,100 pages in English. It's written by Conrad. It's a really good book to have. I have the physical copy because it's also good as a weapon if someone breaks in at night. Yeah, it tells you a lot about how memory works in .NET, but also talks about span and how the implementation works. Yes, you can go. So thank you for listening. I'm going to pop you down there. Goes Mummy. And if you want to follow me or ask questions afterwards, that's where you can find me. And that link is all the slides. So thank you very much. I don't have time for questions on stage, but grab me. I'll hang around if you have questions. Thank you very much for coming.